Okay, welcome back Science 10s to our next lesson in Chapter 5. This is 5.3, and today we're going to be talking about acceleration. So in the last lesson, we looked at speed and velocity. Speed was a scalar and velocity was a vector. These were the same value when something was traveling in a straight line in one direction, but when the direction changed, we saw that the velocity and the speed were no longer the same. We're going to consider things going in a straight line for this lesson. So I put that at the top here, straight line motion. And in that case, I'm going to default to the velocity equation because sometimes it matters if we're going to the left or the right or north or east. So I want to consider direction. And we used this equation. The velocity, the arrow means that it's a vector, is equal to our displacement. So that says change in position over change in time. So we use this equation to figure out how fast something is going, and say we have this for a car and we calculate the displacement over the time that it took to change its position that much, and we get a number like 100 kilometers per hour. Now that is describing one set velocity of 100 kilometers per hour. So when we're using this equation, we're assuming that that's what it was traveling at the entire time. This is called constant velocity, that it's staying at 100 kilometers per hour the whole time. The other word for this is uniform motion. So that's what this equation is for, constant velocity and uniform motion. However, things can't always be in uniform motion. We know that this car is moving at this point, but at some point it must have been stopped before it started traveling at 100 kilometers per hour. And it has a constant velocity of 0 here when it stopped and 100 here when it's traveling quickly. But in between there, it would have had to change its velocity from 0 to 100. And that's what we're going to be looking at today. When we have a changing velocity, either speeding up or slowing down, this is not called uniform motion anymore. It's called accelerated motion. And if we use this equation of v is equal to d over t for a changing velocity, we actually looked at this first when we said if something was changing direction. And if something's changing direction, it is changing velocity. You might remember from the last lesson, if it went west a certain amount, then east, that is a changing velocity because we're changing the direction. We looked at how this formula applied to those situations, and I think we had an example where we went 10 kilometers one way, 10 kilometers back, and we got a value of 0 because that was representing the average. So that's what this formula is going to do. It works well for constant or uniform motion, and if it's used for an accelerated case, it's going to give you the average number. But we're not really that interested in the average number. We want to figure out what's happening at those specific moments in time or how fast it's speeding up or slowing down. So what's going to give us a lot more information about acceleration is the equation we're going to look at today. Okay, so on this slide is the notes for accelerated motion. Acceleration again means a change in velocity. That's important to remember that definition. And this is the equation. So we have A is equal to V over T. Now let's look at those symbols as well. Remember the arrow on top means that it's a vector. So acceleration is a vector. It matters the direction that we're going to be accelerating. There's an arrow over top of the V, that's velocity, which is a vector. And then we have this triangle, and hopefully you remember from before, that means change. So it says we have a change in velocity, and there's also change here on the bottom, which is a change, change in time. So how much our velocity is going to change over time. Now, in previous equations, like the one that was v is equal to d over t, we just kept it that way. But if I'm looking at this change in velocity, we're actually going to rewrite it to this. This says vf minus vi. That f right there stands for final, and the I right here stands for initial. So all this is really doing is it's trying to find that change in velocity. How fast are we going at the end compared to how fast we were going at the start? And then the arrows there just mean vector as well. Now, even though this equation seems a little bit simpler, this one's going to be a lot more useful for us because sometimes it's going to ask, well, how fast is it going after it's accelerated? Or how fast was it going at the start before it accelerated? And so those are going to be useful for calculating VF or VI. So I think that this formula is really the only one you should be using for accelerated motion, unless it's asking for average velocity, which again, we would use just V is equal to D over T. So I also want to look at the units here. In the numerator, we have the change in velocity. So say we had a final velocity of 10 meters per second and initial velocity of 2 meters per second. When we subtract those, we would get 8 meters per second is how the velocity changed. So our numerator is going to be measured in meters per second, okay? But now we're gonna say, well, how much did that change occur, that 8 meters per second? That changed over how long? Maybe that changed over 2 seconds or 3 seconds. So we're going to be dividing by time, which is also measured in seconds. So this is meters per second per second. So it's meters per second 2 times. So how we're going to write that is, as it's kind of covered there, but meters per second squared, meters per second per second. And that's going to be our unit for acceleration. Technically, you could do kilometers per hour, per hour, and then divide by hours to get kilometers per hour squared. It's just a very uncommon unit to see. Pretty much all the time, you're going to see it in meters per second squared. And so it's going to be useful to turn your velocities in kilometers per hour into meters per second by dividing by 3.6, which I mentioned in the last video. But let's try an example with this equation. And so I just looked up the speed for a car. This is a Tesla Model Y. It goes from 0 to 100 kilometers per hour in 5 seconds. And so we're going to try and solve first, what is the acceleration? So if we're ever trying to solve for acceleration, we only have one formula. With acceleration, that's A is equal to VF minus VI over T. Okay, now I gotta see what I'm solving for is A, and it's already rearranged for A. I don't need to move anything around, which is nice. I need my VF minus my VI. So VF is V final, or at the end, and we know it's going 100 kilometers per hour at the end, and at the start, it's going 0. Now, we could just put in 0 and 100, but this is also changing over 5 seconds, and we notice our unit is in kilometers per hour here. We don't want kilometers per hour per second. And like I said before, it's most common to represent acceleration in meters per second squared. So I need to change that kilometers per hour into meters per second. It's really not too hard to do. We take 100 kilometers per hour and we divide by 3.6, and that should give us our number. You plug that in your calculator, you should get 27.7 repeating meters per second. So now let's put that into our equation, 27.7 repeating. Keep all that number in your calculator, all those sevens. Then minus the initial velocity, which is 0 kilometers per hour, is also 0 meters per second, so we don't really have to do much there. I'm going to write here that this is meters per second. Always good to write that in when you're writing down your numbers. And divided by 5 seconds. Okay, when I'm typing that into the calculator, I'm getting 5.5 repeating meters per second squared for our answer there. Okay, so that's how we calculate acceleration. Next, it's going to be a little covered by my writing here, but it says after this initial 5 seconds, the car then continues to accelerate, but at a lower rate. It accelerates at 4 meters per second. Let me switch colors here so we can see it better. 4 meters per second squared for an additional 5 seconds. So for 5 seconds, it gets up to 100, and we see that it was accelerating at 5.5 meters per second squared. And now it's going to continue accelerating for another 5 seconds, but at a little bit slower acceleration, 4 meters per second squared. What is the final velocity after all of this? Okay, so this is accelerated motion. So I have to write A is equal to VF minus VI over T. But now it's not asking me for the acceleration, it's asking for the final velocity, which is right here. Now we have to rearrange this formula. Just a reminder that for rearranging formulas is really similar to solving algebra questions. We want to follow bed mass, and that's when you're solving an equation. For rearranging it, we want to do it in the reverse order, and whatever we do to one side, we have to do the other. It's pretty much the 2 rules. Reverse bed mass, what you do to one side, you have to do to the other, and the operations that you're doing are whatever's going to cancel what is happening to the variable you're trying to solve for. Okay, so VF, we want to get that by itself, and we have VI is being subtracted from it and T is being divided from it. You think, well, what do I do first? Do I get rid of the VI or do I get rid of the T to try and get VF by itself? It's very common that people go to the VI first because they're thinking, well, I'm going in the reverse order of bed mass. I should do addition, subtraction first. However, when we have a numerator and a denominator, that means this whole number on the top, everything up top, divided by everything on the bottom. We just never write brackets there, but that's what we mean with a numerator and denominator. Everything on top divided by everything on the bottom. So really there's brackets there written around the VF minus VI. We just never write them. So that's tricky about this equation. So what that means is we have to get rid of the T first because we're not going to go into those brackets, which is the last part of bed mass. Okay, so we're going to get rid of T first. How do we get rid of T? VF is ultimately being divided by time, so I need to cancel that out by timesing by time. All right, multiply and divide by time, it cancels out. Whatever I did to that side, I have to do to the other. So I'm going to rewrite this as T times A is now equal to VF minus VI. There's nothing except those brackets or those two terms now. So now I'm going to go in there and I have VF minus VI. How do I get rid of VI? Well, VI is being subtracted, so the opposite is plus. So I'm going to plus VI. That will cancel it out over here. If I add it on that side, I have to add it on this side as well. I could put it on the left or right. Just for room, I'm going to put it here. I'm adding it to this side. Okay. And now I'm rearranged for VF. I just need to plug in my values. So I'm going to put in the time as 5 seconds multiplied by, it says it's going a little bit slower now for acceleration, or a little bit lower acceleration, 4.0 meters per second squared. Okay. All right. So now I plug those into the formula. This is going to give me 20 meters per second here, and 27.7 meters per second stays there. I'm going to add those two numbers together, and I'm going to get an answer of 47.7 repeating meters per second. And this is in meters per second because this is talking about our velocity. We took meters per second squared times by seconds and got meters per second for this answer right here. So this is a velocity. It's in meters per second, not meters per second squared. That's just for acceleration. Okay, so really just one formula, but there was a lot of details in there and things to remember about units and rearranging and stuff like that. I hope it made sense for you. If you have any questions, make sure you ask me them in the live time, and I will see you in the next video.